In this second of 3 videos on the method of characteristics, we're going to look at the variable coefficients case. So that is the case where the terms that are multiplying the partial derivative of u with respect to x and the partial derivative of u with respect to y aren't constants like in the previous case, but are functions of x and y. So we have a function a of x and y multiplying ux, and a function b of x and y multiplying uy. However, we're going to restrict our attention to cases a little less general than the tricky general case, because we're not going to consider a term like this being present, and we're also not going to have any right hand side. So we're just looking at the homogeneous first order variable coefficient equation. So let's jump straight into an example. So let's have a look at this example here. Let's begin by thinking how we would classify this equation. So it's linear or is it non-linear? Well, what are we doing to u? We're differentiating it with respect to x, we're differentiating it with respect to y, and then we're also multiplying it by 2x and multiplying it by 5. Those are all linear operations, so this is going to be a linear partial differential equation. What about order? Well, it's first order because the highest order derivative is first order. We only have first partial derivatives. And how about the coefficients? Well, they're variable because we have this 2x here. So that's important. That's a difference to the case that we've seen before. Also, it's homogeneous because we have the right-hand side of 0 when we've moved everything involving u to the left-hand side. So this is a linear, first-order, homogeneous, variable coefficients equation. So the way that we would start to treat one of these equations in order to solve it is quite similar to how we did with the previous case where we had constant coefficients. So we write it again as the product of two vectors. Remember that the gradient of u is just ux, uy. So multiplying this dot product, we get 5ux plus 2x uy, and this is exactly what we have up here in the original equation. So there is absolutely nothing fancy happening here, this is just a rewriting. But then this is the form that we recognise as a directional derivative. So that is the left-hand side here is the directional derivative of the function u in the direction 5 to x. So this is a variable direction now because it depends on x. And then we say that that is equated to 0. And so if we've got something whose derivative in some direction is 0, then u is going to be constant along curves that have got tangents in that direction. So there's a difference here from the constant coefficient case because this is now a variable direction, it depends on x, and therefore our characteristic curves aren't going to be straight lines, but they are actually going to be curves. So this is a difference in the method. Okay, so we've said that u is constant along those curves that have got tangents in the direction 5 to x. So we're defining some curves by their tangents, in other words the slopes at their points, and that varies depending where we are. So that sounds like a nice calculus problem. And we can formulate it in terms of an ordinary differential equation, because if the tangents are in the direction 5 to x, then they're described by this ODE here. So dy by dx is equal to 2x, that's this, over 5, which is here. So, can we solve this? Well, again, hopefully yes, because this is a fairly straightforward ODE that we can solve just by integrating. So if we integrate this, the left-hand side with respect to x becomes y, and if we integrate the right-hand side with respect to x, we get x squared over 5 plus a constant. Okay, so at this analogous step in the previous example where we got equations for the characteristic curves, we found that they were straight lines, whereas in this case it looks like they're going to be parabolas. So the main message here is really that if we have constant coefficients in our equation, our characteristic curves are in fact characteristic straight lines, whereas for the variable coefficients case we'll actually have curves. In this case parabolas, and let me show you the actual solution. So again, jumping ahead a few steps here, but this is what part of the solution looks like, plotted between -6 or so to +6 along the x-axis, and the same range along the y-axis. And you can see that if we look down from above to see where these black lines, which are the characteristic curves along which the solution u is constant, in other words the height, if we're looking at it from this side, is constant. These are like contour lines again. If we look down on that from above, you can see that those curves are all just a load of parabolas. So that totally agrees with what we've just said, that y is equal to x squared over 5 plus c. So different values of c correspond to different parabolas here. So each value of c, we said, defines a different characteristic curve, and along each of those curves u is a constant, and therefore the function u can only depend on which curve we're on. So in other words, u is a function of c, and we've got an expression for c, because if we rearrange this equation that I've put a yellow box around, then c is equal to y minus x squared over 5. So we can replace c here with y minus x squared over 5. Okay, so that is the general solution. But we've got a boundary condition that we can apply to find out what this arbitrary function f actually is. So let's move on to look at that. So all we need to do now is, as I said, find f via the boundary conditions. So this is our original equation. We had this boundary condition that we haven't yet used, and we're going to use that to find f. So this boundary condition tells us something about when x is equal to 0. So let's see what the general solution becomes when we put x equals 0. Well, if we have u of 0 and y, that's just going to be f of y minus 0 squared over 5. So again, that's just f of y. And we're told that that has to be sine y. So very simply here, the function f is just the function sine. Therefore we can put that into our general solution to get the correct answer for the whole problem. So the solution is that u of x and y is equal to sine, that's putting sine where we had f before, y minus x squared over 5. And that completes that example. So in the next video we'll move on and look at the general case.